Ladies and gentlemen, we have here a talk by Sebastian Starks. Do I pronounce this well?
Yeah,
Yes, Starks. Ich musste das mal im Deutsch sagen. And he's related to the University of Aachen. He did a PhD physics, and he was in a team that developed a fantastic application, as I mentioned earlier on. He developed the app phyphox. Do I pronounce it as well?
I would say phyphox.
Phyphox.
Physical phone experiments.
Okay, yeah. Of course. I'm sorry, I'm not in that kind of department. So. But this application actually gives you other possibilities of the usage of your smartphone, really extending certain borders, to my opinion. So please give a warm welcome here to Stefan.
Okay, yeah, thank you. Thank you for the introduction, and welcome everybody to my talk. Yeah, as you've just heard, I'm a physicist from the RWTH Aachen University, where I developed the app phyphox. Phyphox is an app, for those of you who do not know it already, that uses the sensors in the smartphone for physics teaching. So the idea is that students can use their own phones to do experimentation in class, in the lecture hall, so for schools and universities. I should explain that in contrast to some other talks by me, this one will not be that much about education, because this is the Chaos Communication Congress and this is the hardware track here. So I try to tell you a little bit about the app, a little bit about the sensors that we have in our phones, and yeah, I would really love to get into touch with some, especially people from maker community and from open source communities, to find some connections, how we can get many open source projects together, because I've got so much feedback from teachers, and I think I could also use some feedback from other developers as well. So, I would like to start with a short explanation of what we actually do. So, yeah, as I said, I come from a university, and there we have this introductory lecture for physics students, which is called Experimental Physics 1. And it's a typical lecture, looks like this. We have a fancy new lecture hall by now, but the situation is the same. We've got 370 students this year sitting in the lecture hall, and doing no experimentation at all. There's only one guy experimenting, and that's the professor. And the students are sitting there and are enjoying the whole show like they would enjoy a YouTube video, and maybe they're mildly amused if something goes wrong, okay? And we thought we could change this by using the sensors in the smartphones. We're not the first ones with the idea to use the sensors there, but for some reason we decided to write our own app, which turned out to be quite successful then. So in contrast to the old version, where students just had a look, they now get assignments where they can do their own experiments with their own measurement devices. And to give you an idea what this looks like, I would like to start with the first experiment, which is about centrifugal acceleration or centripetal acceleration, depending on your preferred frame of reference. So the idea is, from a rotation movement, we want to measure the radial acceleration as a function of the angular velocity, so the rotation rate. To do this, we take a regular smartphone, this is an iPhone 8 in this case, and we put it into a salad spinner. Okay, so we get some rotation in there. And, oops, let me just place it in there. And sound is not important, but it sounds nice, I have been told. So here we get the live data from the phone. Already acceleration on the y-axis and angular velocity on the x-axis, if the salad spinner is actually moving. And what you see is the faster I rotate the spinner, the farther on the right you get your data, because that's angular velocity, and also the radial acceleration increases if I'm not going too fast, because then I do not get any data at all anymore. Let's slow down again. And we can fill up the gaps there by going really slow and filling up this part. And in the end, if so who here has a physics background? Okay, some. Oh, more than expected. Great. Because those of you who just raised their hands should not be surprised that we expect a square relationship between the radial acceleration and the angular velocity. Those of you who do not know will believe me from this plot, where on the x-axis we've got the angular velocity squared, and on the y-axis the radial acceleration. We get a straight line, and that's what we would expect. So besides the physics, because this, now not that much about the physics, this is a simple experiment all our students could do. And actually we gave them this assignment. We gave them also a bonus point if they created a video. Don't worry, their consent that we used the video was not related to the point. They first got the point and then we asked for their consent to use the video. And we learned two things from these videos. A, our students do not really have salad spinners, but they've got bicycles and office chairs. But B, and that was the most important thing, it looks like, I mean, these are from this year, where I got almost 100 videos. We actually could trigger them to go out, search for something where they've got a rotationary movement, and they could repeat this experiment. Okay. Another example, which actually changes the course of the lecture a little bit, is a situation where we first give the assignment before we actually before we actually discuss the theory behind this. Which means, in this example, this is a little bit older because we did not get there yet this year. We assigned our students to build string pendulums. They look very similar because we were very precise about how they should build them. And then we had an online form where they could submit the length of their pendulum and the frequency they received from it, that they measured with their pendulum. They should do this for 3 different cases. And the idea was that we did this assignment long before we discussed the pendulum in the lecture, so that they have got a little bit of research experience. And after we collected all the data from then in the lecture we discussed the pendulum. So the physicists were then we do a small angle approximation, solving differential equation, all this theory stuff. And in the end, when we were done, we could tell our students, well, we do not have to do this experiment on stage now, because all of you did this experiment, and we simply can compare the theory that we just derived with your data. And it worked out quite well. So you see most of the white points, which is the data from the students, matches the theory, which is the orange line, except maybe for those 3 who should proceed on a career of theoretical physics. But yeah, so this is also something we got nice feedback from, and this is in principle how we use the app and what it's designed for. There are also, of course, many applications in school. By now, more teachers use this in school than we use it at the university. So we take this into consideration as well. But that's the reason that I'm standing here talking about the sensors on the smartphone. That's the reason that I am trying to access them. Okay, so let's have a look at what sensors we actually have in our phone. I think the first one that most of you will think of when talking about sensors, besides obvious stuff like the microphone, would be the accelerometer. So I think I first explain how the accelerometer works. Okay, so the accelerometer in your phone is actually a so-called MEMS device. MEMS is MEMS, stands for microelectromechanical system, and it looks roughly like this. It's a simplification. If you search for actual MEMS devices, simply search for MEMS and accelerometer, and you find some pictures. They usually are a little bit more complicated, although the accelerometer is not that much more complicated. It consists of an orange case. Yeah, well, so far so obvious, but also 2 contacts, the blue and the red one. And the important part is this silvery structure here, or the metallic structure, which is under-edged. It's a bit hard to see on this picture, but it's actually floating. It's only attached to the sides. You see a light in between here a little bit. So if you move around the accelerometer, the inner part can actually move. So let's do this. So at each point where the device is accelerating one direction or the other direction, due to the inertia, the metallic part in here is distorted or moved into one direction. And we can measure the amount by which it is deflected by this movement with the 2 contacts by measuring the capacity between these structures. Okay, so that's the principle of the accelerometer in there. One thing to mention at this point is that it's in a sense of physics. It does not really only measure acceleration. It measures acceleration. You see it in this image. Okay, if the device is accelerating, we get some data. But if you imagine we take this device and rotate it like this, then of course you also get a deflection of the metallic part by gravity. Okay, so gravity is pulling it down as well. And that's the main reason that the accelerometer is in there, because the developers and manufacturers of the phones are not really interested in measuring acceleration. At least there are not that many use cases for it. But instead, what they want to have is an indication on which direction is down or which direction is up. So when you rotate the screen of your phone, actually they can rotate the content of the phone as well. Or with this, you can also then control video games by tilting your phone and stuff like this, because gravity also deflects the accelerometer, so Earth's acceleration, which I try to avoid because from didactics point of view, this is a nightmare to distinguish these both. But the point is that we can detect rotations like this. And this is pretty much in every phone. I mean, this is not really a statistic. This is just the first pie chart we have about the availability. I have never encountered a single phone or a tablet that does not have an accelerometer. So if anyone ever encountered some special device, some very unique device that doesn't have one, let me know, because I would be interested in this. At least I do not know of any device on which phyphox actually runs, which doesn't have an accelerometer. A bit more interesting is which data rate we can achieve. So most accelerometers have several hundred samples per second. Actually, the fastest ones go up to 500 hertz. And, but there are also many devices that only do 100 hertz, so 100 values per second. These are mostly the cheaper Android devices and all the iPhones. So I think the internal accelerometer will do more on an iPhone, but I have to admit, at some point, I can understand why they might limit this, but on an iPhone you get 100 hertz. That's the limit from the API, what you can get there. But this is actually quite a lot, and we will later see what we can do with this. And one other point about calibration of this thing. Actually, for all the sensors, you get reasonable units from the system. So the acceleration is given in meter per square second. I just realized that I forgot the units. That's something I would really tell my students. But so on the x-axis, it's in meter per square second. And you see that there's a wide range of values that you get there. So this data is from our sensor database. I will mention it later as well. This is contribution from our users, what data there is. This is only absolute value that we get from resting phones. And we would expect 9.81 meter per square second for Earth's acceleration. There's some local variation, but not on that scale. So do not expect your sensors to be well calibrated. Also, if you've got any app that tells you you can push a single button and then it calibrates your sensor, don't trust it. It's not that simple. These sensors may have different errors on each axis. They are all 3D sensors, so we've got an X, Y, and Z axis. These errors can be a linear error, so you have to multiply a correction. It could be an offset, so you would have to add a correction. And on top of this, the entire device could be tilted within your phone. Okay, so actually, if you look into the data sheets of the accelerometer, they have some tolerance on how much they might already be shifted or rotated within the package. And when soldering it into the phone, I would assume there will be an additional error. I've seen so many different errors on different phones. It's not that easy to simply calibrate that. Okay. But let me give you an example of what you can do with it, or just a quick look first. So you see in our app, so this is phyphox, okay, I think you got this. You have an entry acceleration with G. That's the actual raw data from the sensor, or as raw as we get it. If I start it, you see if I shake it, you get some readings there. This, for us, it's already great. You can apply it to pendulum and measure the acceleration of the pendulum like this. But something I want to demonstrate is that we can also get the frequencies from this data by doing a Fourier transform and calculating the frequency spectrum of this acceleration data. And to demonstrate this, I brought a little device, old hard disk drive. It says it's broken, but it's still rotating, and that's the important part for us. So if I place my phone on top of it, start the measurement, turn on the hard disk drive, and then you see a peak showing up in the spectrum, and it settles at 120 hertz. If you don't believe me, unfortunately we don't have a camera here right now, you can later have a look. It's supposed to run at 7,200 RPM, which is 120 hertz. Okay? We can even get a time resolution of this. So if I turn it off again, you see how the frequency drops down. And if I turn it on again, there it comes up again, okay? So this is an example of what you can do. It's great for students. They can check if the washing machine at home is working properly, or they can check other things. But usually I do not like to bring washing machines to talk, so I use the hard disk drive here. One other thing you might have noticed before is that we've actually got acceleration with g and acceleration without g. The second one is actually a sensor that removes Earth's gravity. So if I start the one with g, you will notice that down here on the z-axis, you still have the 9.81 meter per square second, which is great because if I rotate the phone, this contribution goes to other axes and we can determine the orientation of the phone. But this is bad actually for didactics because, actually the phone is resting, it's not moving at all, there's no velocity involved, there is no acceleration. So luckily, there's also an acceleration without g, which gives us roughly 0 on all axes unless I actually accelerate this thing. Problem with this is only a virtual sensor. This is a sensor that's fusing the data from the accelerometer with an additional sensor like the gyroscope. So we can actually distinguish between rotating the phone or accelerating it in one or the other direction. Usually you only get acceleration without g if you also have a gyroscope in your phone. I've seen 2 or 3 devices that offer you acceleration without g, even though they don't have a gyroscope. In this case, don't trust them. This is nearly guessing. Okay, so it's they probably have only low frequency filter on top of this, so they're averaging out your movement, and this doesn't really work for anything. Yeah, so that's the accelerometer. Oh, one other thing I want to mention is if you look into the API to access the sensors yourself for some reason, you will notice acceleration without g is usually called linear acceleration. In our app, since it's made for teaching, we decided to call it with and without g. So if you find accelerometer, that's the one with g, and linear acceleration is the one without g if you look at other apps or the API. Okay, next up, I already mentioned this one, is a gyroscope. If you have some physics background, then when you think of a gyroscope, you're thinking of a device that's spinning fast, so it has some angular momentum, and then usually you want to have it to be heavy and to have the weight at a large radius, so it's got a strong moment of inertia, so that you get, when it's spinning fast, a strong angular momentum, and due to the conservation of angular momentum, these spinning devices can keep an axis regardless of rotating the frame around it. That's what I was thinking about a gyroscope, what I think is a gyroscope, when you just give me the term out of context. Of course, a heavy, huge, fast-spinning device is the last thing you want in your phone, so that's not what's meant with a gyroscope when people are talking about gyroscopes in your phone. Instead, there again, you have a MEMS device. So again, a micro-electromechanical system. You will notice this looks almost exactly like the accelerometer. If you look for real devices, those are actually much more complicated because they need some specific geometry to make sure that they do not act like an accelerometer. But the principle is easy to explain with the same geometry. So we again have this floating metallic part. And we've got 2 contacts. So again, we've got a part that can wobble in this direction here. But on top of this, we've got a motion that's perpendicular to this. So this is now not depicting the motion of your phone, but this is depicting a vibration that the gyroscope does by itself all the time. So there are different ways to build them. Some have a rotary motion, some have this linear motion. Also, the way to create this motion makes this device so much more complicated, but in principle, it's a similar structure which is vibrating forth and back. And now if we add rotation to it, it's a little bit hard to see it as it's rotating. The inner part now suddenly gets deflected. Let's change the frame of reference. So let's get the camera in sync with this device. What you now see is that the inner part is moving left and right, although the device itself is only moving up and down. And the reason is, I don't want to deduce it entirely here, but most of you probably have heard of it. This is the Coriolis effect. So yes, in fact, your phone is determining the rotation rate of your phone, not the actual angle, but the rotation rate or angular velocity due to the Coriolis effect, which is just mind-blowing if you do some of the calculations. There are some manufacturers on the internet which claim that they can detect a movement of the order of magnitude of a single atom. And I believe them because we use similar structures in solid-state physics, so that's possible. If you want to try it, just turn on the gyroscope on your phone and do a slight rotation like this, which is about the z-axis, the one perpendicular to the display. You can detect really slow rotations with this, and think about the fact that this is done using the Coriolis Effect, and yeah, it's just mind-blowing, I think. So this sensor is a bit more available. Actually, almost 80% of the phones have them. This has become significantly more since Pokemon Go. The reason is when this game came up, suddenly people noticed that there's a device called a gyroscope, and if it's not present, they did not have this AR mode where you can actually take pictures of the nice, cute Pokemon and so on. So this is when many people noticed it, and the manufacturers decided, okay, let's just throw in the gyroscope as well, because it's not that expensive. In fact, usually it's on the same chip as the accelerometer. Then they're sold as one thing. It's an IMU, inertia measurement unit. Not important, that term, but it's quite a common thing. And the sensor rates look pretty much the same. You mostly notice a dip in the 100 Hertz regime because those are the really cheap phones which then also don't have a gyroscope, but most of the phones achieve higher rates. Again, since we were laughing before, the iPhones also are here again at the 100 Hertz. Wouldn't make sense to have the gyroscope faster at this point. Yeah, but that's it about the gyroscope. You've seen it in action in the salad spinner. And that's one of the sensors you do not really see that often directly, but which is mostly there to assist other things that you do where you need to get smooth motion, like controlling games, AR, and actually removing the Earth's acceleration from the accelerometer. Next up is a magnetometer, which I think is a more obvious sensor because that's your compass in your device. So when you're doing navigation with GPS in your car, it's a simple thing. GPS gets a position, you get a sequence of position as you're going, and from the sequence of the positions, you get the direction you're moving in your car. And your phone is attached to the dashboard, at least I hope so. So it's pointing in the same direction you're moving, everything's obvious. But if you